start the share screen. Usual routine. Go over here. All right, let's enlarge this. So what I've got here is a summary of some of the things we started with in the last lecture. It wasn't very much. I think to review it just briefly, we are interested in Green's functions for the energy dependent Schrodinger equation, that's to say energy eigenvalue problems, because the solutions of positive energy for scattering problems that we want to solve are in fact energy eigenfunctions. They're unbound solutions. But that's what we want to solve. So we need a Green's function for the energy dependent or time independent Schrodinger equation. However, it turns out that in order to get there, we have to pass through the subject of Green's functions for the time dependent Schrodinger equation. And so we started out by at the end of the hour last time by talking about that. And I've summarized some of that here on this a piece of paper. So up at the top here, I've got the homogeneous time independent, let me say it right. This is the homogeneous time dependent Schrodinger equation, just rewritten with the two terms brought over the same side. So psi of x and t is a solution. I'm writing this as if it was a one-dimensional problem, which is enough to give you the idea. The equation becomes inhomogeneous if we put a source term on the right-hand side, which I'll call S. And I explained last time about why it is that we introduce source terms. And in fact, the equations we're really interested in solving are really homogeneous. But we'll come back to that later on once we get the Green's functions. I don't think we'll get beyond getting the Green's functions tonight. But in the next lectures, we'll certainly look at that. In any case, what we call a Green's function for the time dependent Schrodinger equation is in general is a function I call f here. It depends on two space-time points, one which I call the field point, it's x and t, and the other I call the source, which is x prime and t prime. And the definition of such a Green's function is that it satisfies this given differential equation. Here's the wave operator on the left-hand side. It acts on the Green's function and produces on the right-hand side delta functions, space-time delta functions, you can see here. The IH bar that appears there is just a conventional factor, but it's basically because we also have an IH bar on the DDT term on the other side. Anyway, the Hamiltonian here is the Hamiltonian operator, and it's understood that it acts on the field parts of F, not the source parts. In fact, for the Hamiltonian operator, let's be explicit about what it is. Let's write it as a differential operator, the usual one for a 1D quantum problem. Let's just write it out. It's kinetic energy plus the potential energy. You can allow the potential energy to depend on time, because initially I'll be allowing, this is a time dependent problem, so we can do that. I'll go ahead and do it. In any case, that's what the H means here. So to repeat myself, we will call any function f of these four variables, or this pair of space-time points that satisfies this differential equation. We will call it a Green's function for the original, either of these two equations gets used in the inhomogeneous equation. And if we find such a Green's function f, then the general solution of the inhomogeneous equation is given by this formula here. It's the solution psi of x and t is a solution of the homogeneous equation, as to say what we have up here. In fact, I could put an H on this here just to emphasize that that's a homogeneous solution. This is a solution of the homogeneous equation plus an integral. And the integral is taken over the source distribution, both in space and time. That's supposed to be an S here for the source of x prime d prime. And basically the Green's function is just the kernel of the integral transform that you carry out in order to get the wave field, the final wave field. Okay. Now Green's functions are not unique because all it has to do is satisfy this equation. this equation, defining a Green's function, is itself an inhomogeneous wave equation because it's got a non-zero right-hand side. And as I indicated last time, part of what I'm saying here is that if you can solve this equation with a delta function driving source term, then by integrating over delta functions weighted by the function s, that's what this integral is, you can construct the solution to any inhomogeneous differential equation. That's the idea. However, solutions to inhomogeneous equations are never unique because you can always add a homogeneous solution to it, and it doesn't change the fact that it solves the equation. And so that applies to the Green's functions as well. They're not unique for the same reason. Having found one Green's function f, I could get another one f prime by adding an arbitrary homogeneous solution, a function of x and t. And I could parameterize it as a function of x prime and t prime any way I wanted to, as long as it was a solution of the homogeneous equation for all values of the parameter. So in any case, this is a way of saying these f functions, these Green's functions, are far from unique. In physical applications, we usually pick out Green's functions that we need for a particular problem by means of the boundary conditions that they satisfy. And in fact, that's what we'll be doing here tonight. All right, so that's kind of a review of what we did last time. Are there any questions about that before we go on? My presentation of this subject involves a fair amount of taking things for granted that this is actually going to go somewhere interesting, because I'm asking you to take a fair number of stuff on faith at certain points, but I'll actually develop it and carry it through in detail as we proceed. So let me get just a single sheet here and center it. So now the problem is, how about these f's? How do we find them? Well, I'm going to start by giving you an example of an f that works. This is called the outgoing Green's function. It's also called the retarded. It's another name for it. There's a variety of names for it. I'll generally call it the outgoing Green's function. And instead of calling it f, I'll call it k plus. And it's a function of xt and x prime t prime. All Green's functions are a function of those four variables. And it's defined this way. It's defined as the Heaviside step function, theta of t minus t prime, multiplied times the matrix elements between x and x prime of the unitary time evolution operator, which depends on two times, because we're allowing the Hamiltonian to be time dependent. I'm not really going to use time dependent Hamiltonians, but the formalism allows for it. So to be general, we'll allow it here as well. In some ways, it's simpler to write things out that way. All right, so I claim this is a Green's function for the time dependent Schrodinger equation. The Heaviside step function is defined in the following way. If I have a variable tau, theta of tau is defined as equal to 1 if tau is greater than 0, and it's equal to 0 if, greater than or equal to 0, and it's equal to 0 if tau is less than 0. So if we plot it, the plot looks like this. Here's tau, here's theta of tau, and it's 0 for negative tau, and then it rises up abruptly to 1 for positive tau, and then it just continues that way. So this is a unit step function. And the main property of interest to us is that the tau derivative of theta of tau is a Dirac delta function. So the theta function is the Heaviside step function is really the integral of the delta function. The explicit formula is this: is that theta of let's call it theta of tau is equal to the integral from minus infinity to tau dt of delta of t. I'm sorry, yeah, this is upper limit is tau. Let me write it more carefully. Upper limit's tau. So you can see that if tau is less than 0, then the delta function is not part of the range of the integration, and so the answer is 0. Whereas if tau is greater than 0, then it does capture the delta function, and so the answer is 1. That's how you get this. In any case, that's the Heaviside step function which appears here. Now then, so the first thing I'd like to do is to show that this k plus actually is a solution of the defining equation for a Green's function. Before I do that, however, let me mention that this matrix element, which appears over here, is what we call last semester, we just called it K, of x and t and x prime t prime. And we gave it a name, we called it the propagator. And you may recall we went through this in connection with path integrals, or the path integral is an expression for the propagator. Let me separate this off like this so it's not going to get confused. So the k plus is the same thing as the k without the plus, except it's multiplied by the step function. Now what the step function does is it makes the answer vanish unless t is greater than t prime. So if t is less than t prime, the answer is 0. So that's all it does. In any case, let's take this and let's see if it satisfies the defining equation for a Green's function. So for that reason, for that purpose, we need to apply IH bar ddt minus h acting on k plus x and t, x prime and t prime, like so. What does this give? So let's look at the IH bar ddt first. This is going to act by the chain rule. There's two time dependencies. There's one there and there's one there. So we're going to get two terms by the chain rule. Differentiating the theta first, this gives us IH bar times the Dirac delta function of t minus t prime times the same matrix element x u of t comma t prime x prime, and then the IH bar ddt is going to act inside the matrix element on the u. Let's write this out. This then becomes a plus the Heaviside step function of t minus t prime x IH bar partial of u with respect to t prime with respect to t x prime, like so. But then there's also the h term, and the h term is then we can write it like this: is put a bracket here. We have minus h acting on x u of t prime x prime, like so, where x is understood to be, as I mentioned earlier, the differential operator. Let me bring that back. It's just the Schrodinger operator. Here it is. Here's the h. It's this operator acting on the x and t dependence. So acting on this matrix element, the x dependence is there and the t dependence is there. Let me introduce the operator I'll call h hat, which is different from the differential operator because it's written as a Hilbert space operator as p hat squared over 2m plus v of x hat comma t. It's really the same operator, but what you'd write for acting on kets rather than wave functions. And this last thing that you see here is the same thing as with the overall minus sign of x and x prime sandwiched around h hat multiplying onto u of t prime. This is just following the rules of how you take an operator out of a matrix cell and convert it into a differential operator. In any case, the result is that this IH bar du dt is the same thing as h hat times u hat of t comma t prime because of the differential equation which u satisfies. And as a result, this term cancels with that term. And all that's left is the first term, which is up here, this term. Let me underline that. So let's turn our attention to that term. Now that term is multiplied by a Dirac delta function. And so that vanishes unless t is equal to t prime. But if t is equal to t prime, then the u operator in the middle becomes u of the same 2 times t prime, and that operator is just equal to 1 because when the 2 times are equal, the evolution operator is just the identity. So what this matrix element's left over is, if I write it down here, it's just the scalar product of x with x prime, and that's the same thing as the Dirac delta function of x minus x prime. So the result is the right-hand side of this becomes equal to IH bar from here, that part, times the delta function in time, t minus t prime, which is that part, times the delta function in x, which is the rest of it. And that was the defining equation for a Green's function. And so we see that this k plus defined in this manner actually is a Green's function for the time-dependent Schrodinger equation. Now this is kind of interesting because it means that what we call the propagator, last fall we called it k. By the way, other people call k plus the propagator, or sometimes they call them both propagators. So if you hear the word, you have to be clear which one you're talking about. They only differ by the multiplication by this theta step function. That's the only difference between them. The k plus, as I just demonstrated, actually is a Green's function, however, and the k is not. However, you'll recall from last semester what we used the k for was for advancing wave functions in time, given initial conditions. This becomes the kernel for doing that, where you integrate over the x prime variable and the t and the t prime parameters. Whereas in this context, the k plus, almost the same as k, is the kernel of the solution for the solution of the inhomogeneous equation. Here it is. Here's this f replaced by k plus, you see. And now you integrate over both k prime and t prime, excuse me, x prime and t prime. So in any case, this propagator k, or the k plus, which is closely related, play a kind of a dual role in quantum mechanics. They also use for solving inhomogeneous equations. All right, so this k plus is a Green's function. Now let's examine its properties, list its properties, because it's not, because as I said, there's many Green's functions, and this one has certain special characteristics. So in the first place, k plus of xt and x prime t prime has the following properties. One of them is that it equals 0 for negative times, for t less than t prime. And that's simply because of the Heaviside step function forces that. So that makes it easy. For positive times, well, here's the Schrodinger equation, which the k satisfies. You have to follow this line down to see the right-hand side. What you can see is the k plus in the field variables x and t, because that's what the h operator acts on. If you're not at t equals t prime, if you're either before or after, then k plus is a solution of the homogeneous Schrodinger equation. In other words, it's a solution of the time-dependent solution of the Schrodinger equation, the usual Schrodinger equation, in the variables x and t, both for negative times and for positive times. It's only right at t equals t prime that you have a non-zero right-hand side. Now, in fact, the fact that k plus is 0 for negative times, I just pointed that out. So the fact, and that is a solution of the Schrodinger equation, but doesn't tell you very much. On the other hand, for positive times, the answer is non-zero. So this thing here, regarded as a wave function in the field variables x and t, parameterized by the source variables x prime and t prime, actually is a solution of the time-dependent Schrodinger equation. So second property is that it solves the t-dependent Schrodinger equation for positive times. All right. Now then, the solution of the time-dependent Schrodinger equation, usually the way we would get it is we'd have some initial conditions and then we'd evolve forward in time. So this raises the question, what are the initial conditions? So that leads to the third property we want to look at. Let's let t approach t prime. T prime was the initial time. Let's approach it from the positive side. I'll write it as t goes to t prime plus of k plus of xt and x prime t prime. What is it? Well, to go back to the definition, if you have positive times, the step function is 1, so it doesn't do anything. If you approach from above, it stays 1. So we just need the limit of the k without the plus as t goes to t prime. But if t goes to t prime, then this u goes to 1, and then the xx prime scalar product is a Dirac delta function in x and x prime. So this then becomes equal to Dirac delta function of x minus x prime. Now, this leads to an interesting way of thinking about this outgoing propagator, and that is the following. We say that the outgoing propagator is 0 for negative times, and for positive times, it's the solution of the time-dependent Schrodinger equation with an initial condition, which is a delta function at the location of the source point, delta of x minus x prime. So if you have some source point x prime in mind, here's your x-axis, and you've got an x prime here. You just imagine an initial condition here, which is a delta function, and you just call that psi of x comma 0 t or psi comma t prime. T prime's initial time here. and these are wave function psi, and you just evolve that in time, and you get, and what you'll get is the Green's function. So that's a way of thinking about it. All right. In any case, there's your time-dependent Green's function for the outgoing Green's function. So we proved that it's a Green's function. We got various properties of it. Now then, let's now use it for solving. Let's plug it into the formula for solving a wave field for the inhomogeneous Schrodinger equation. It's going to be psi of x and t is the homogeneous solution, psi homogeneous of x and t plus 1 over IH bar. I'm just copying my earlier formula, but I'm going to put in the k plus instead of an f. So we have integral from minus infinity to plus infinity dt prime and integral dx prime. And then we have the step function theta of t minus t prime. And then we've got the k without the plus subscript of x and t and x prime and t prime. And then we've got the source evaluated at x prime and t prime. Okay. So this is what we get by just plugging in the formula. Now, on the other hand, because of the step function theta of t minus t prime, it means the integrand vanishes if t prime is greater than t. And so the result is that we can, if we like, we can take this upper limit of infinity and replace it just by t, upper limit of t, because that theta function will drop, we'll cut it out anyway. And then having done that, we can cross out the theta function because it isn't needed anymore. And this then gives us an expression for the propagation that involves only the k without the plus subscript on it. So that's a useful formula too. Now I'd like to take this expression and impose the condition of what's called causality. Causality basically means that when it's a principle which if we impose the principle of causality, what it means is that the final wave field cannot be, it can't be non-zero until the source is turned on. Or to say it another way, is that if the source of x and t, let's say, equals 0 for t below some turn on time, I'll call t0, it vanishes before t equals t0, then for a causal solution, we require that psi of x and t also be equal to 0 for t less than t0. Psi cannot appear until the source turns on, in other words. Now, if we impose the condition on causality on this equation, what it means is that the homogeneous solution has to vanish. And the reason is that the homogeneous solution, being a solution of the free wave equation, if it's non-zero at any time, it's non-zero at all times. You know, you can't make the solution of the Schrodinger equation go away. I mean, you can't make it go to 0. The time evolution operator is unitary, so the square of the wave function remains 1 for all times, positive and going back to minus infinity. So there is no negative time, no matter how large t gets negative, for which the psi homogeneous is equal to 0. On the other hand, the rest of this integral is if s satisfies this condition, if it didn't start before t0, then this integral vanishes for t less than t0. And so therefore the conclusion is that psi homogeneous must equal to 0. So therefore, for a causal solution, we have this formula, but without the psi h. And let me write that out then. So I'll call this the causal solution. We've got psi h of x and t is equal to 1 over IH bar, the integral from minus infinity to t dt prime, the integral over x dx prime of the k without the plus or minus subscript xt x prime t prime, and then the source x prime t prime. And so that's kind of a useful result, which in fact I'll come back to a little later. All right, now then, so this is the story in the outgoing Green's function. The outgoing Green's function, to summarize, is k of x and t, x prime t prime, is step function theta of t minus t prime times, I'll just write it here as k of x and t, x prime and t prime, the k without the plus subscript. And this is the same thing as the matrix element x and x prime sandwiched around the unitary time evolution operator. It's equal to that, okay? Now, what I'd like to do is introduce another Green's function, which will be useful. which is called the incoming Green's function. By the way, the difference between any two Green's functions is a homogeneous solution. That's because the difference between any two solutions of the inhomogeneous equation has to be homogeneous, because when you subtract, the driving terms cancel out. So the difference between the outgoing and incoming Green's functions is actually a homogeneous solution. Nevertheless, I'm just going to quote for you what the incoming solution is. Oh, let's see, this outgoing should have had a plus on it right there. The incoming Green's function is called k minus of xt x prime t prime. And it's given by the minus sign, Heaviside step function. And now instead of t minus t prime, it's t prime minus t multiplied times the matrix element of the time evolution operator, like so. Okay, that's the incoming Green's function. So as far as properties of k minus are concerned, what are they? The first one is that k minus is equal to 0 for positive times for t greater than t prime. The second one is that it satisfies the Schrodinger equation in the field variables for really for any t not equal to 0, but for positive times it's 0, so 0 is a trivial solution. So it's for negative times is what we're really interested in, and satisfies it for negative times. And the third one is that the limit as t approaches t prime from below, where the theta function is always 1, gives us with a minus sign of delta of x minus x prime. Okay. So now, that's these are the two most useful Green's functions out of an infinite number of choices for the time-dependent Schrodinger equation, the incoming and outgoing, and here's their specific properties. Let's go back to the incoming Schrodinger equation, the incoming Green's function. And let me go back to, it's kind of all over the map on this piece of paper here, but here's the equation it satisfies. There's a Schrodinger operator, there's k plus, following the line down, that's equal to delta functions on the right-hand side. So I want to present to you a water wave analogy of this Green's function, because it gives you a physical model you can think about and helps you visualize what the Green's function itself looks like. You might think it's hard to visualize the Green's function because it depends on 4 parameters, but if you think about it in this water wave analogy, it's not so hard. So it goes like this. Let's suppose we have a lake of water which has been quiet with no waves on it since the beginning of time. And then at time t prime, where this delta function is non-zero, we go up to the lake at location x prime. Remember, that's a source point. And we drop a stone in the water at position x equals x prime. Or we poke our finger in the water just once, point, like this, at that one point. So that's the source term. It's localized in both space and time. And the k plus is the solution of the wave equation for positive times after that impulse that's given at that location at that particular time. So the wave which is radiated outwards is the Green's function. And if you've ever thrown a stone in the lake, which I assume all of you have done, you've seen the Green's function and you've seen how it propagates. It's a wave that in waterways it disperses as it travels, but it's basically a wave pulse that radiates out initially anyway in a spherical wave pattern and propagates outwards. So that's your way to visualize what the Green's function is. Here's another example. It's similar. All you need is some source which is localized in space and time. An earthquake, especially small earthquake, is highly localized in space and time. Big earthquakes can last a long time, but small earthquake is abrupt and short, and also spatially localized. And so what that does is that generates sound waves in the earth, and they're picked up by seismometers that are stationed all over the earth. Well, what those seismometers are actually registering is the Green's function for sound waves in the earth, where the source position and the source time were given by the location and time of the earthquake. So there's another example that allows you to visualize the Green's function. That's what they're really measuring, is Green's functions from various different source points in the earth. All right, so that's the idea of the Green's function. that's the idea of the outgoing Green's function. The idea of the outgoing Green's function is we had a quiet lake, we poked it at one point at one time only, single delta function, and the radiated wave is the Green's function. What about the incoming Green's function? Can we interpret that in a water wave example? Well, this is a wave function which is non-zero for all negative times, but it's zero for positive times. So here's what, and also it has this limit as t approaches t prime from below, it turns into a delta function. So what you imagine is that there's this wave field rattling around this lake going back to the beginning of time. And it just continues to do whatever it does to create waves on this lake, which bounce around and interfere with one another. However, as the time starts to approach this prime t minus from below, the waves begin to focus on the location x prime. And as you reach x equals x, excuse me, as you reach t equals t prime, those waves focus into a delta function, really with a minus sign, to create a completely localized disturbance in the manner of a delta function at one location at one time. Now what happens is our finger comes up and we intercept that delta function, we absorb all the energy from it. And then what happens is that the wave is, the lake is quiet with no waves at all for the rest of eternity. Okay, so that's the physical picture, if you can call it that, of the incoming Green's function. Now it's easy to throw stones into lakes, but so outgoing Green's functions are easy to construct experimentally, but the incoming Green's function is impossible to construct experimentally. Nevertheless, it's useful for theoretical reasons, as we'll see, and that's why I'm bringing it up. Both of them play an important role in the theory of the subject. All right, okay. Let's see, I just have a couple more comments about these Green's functions. The Green's functions are associated with operators. The Green's, let's take the plus Green's function, the k plus of xt and x prime and t prime. Let's denote this way as the matrix elements between x and x prime of an operator called k plus with a hat. And the k plus depends on the times, but it doesn't depend on x. So we can take this as a definition of the operator k plus from the Green's function. It's similarly to k minus, we have plus and minus sign on here. Both of them are defined in that way. And if we define so I'll put the hat here on the operator. So if we define the operator that way, then some of the relations that we've written down already, for example, let me do just the k plus. The k hat plus as a function of t and t prime, our earlier definition of it now can be written in this way, as the step function theta of t minus t prime times the unitary time evolution operator t comma t. It should be t comma t prime, like so. So it's a step function times u. With the k minus, you reverse the t and t prime and put an overall minus sign in there. So this defines what I'll call the Green's operator, for the time-dependent Green's operator. And the Green's function is just the matrix elements of it. The Green's operator has a number of advantages over the Green's function. For one thing, we might have a system that doesn't even have an x variable. It might be a spin system, for example, in which case the operator makes sense, but this equation doesn't, because this was chained to an x representation in a 1D quantum problem. So by working with operators, we can deal with more general quantum systems. It might be a three-dimensional problem. It might have multiple particles. It might be relativistic. It might be a field theory. So all these generalizations can be handled in the operator formalism, whereas this is chained to a specific simple model. So I'll be doing a lot with operators rather than functions, but they're related one to another in the cases where you can take the matrix elements like this. All right. So that's one comment, is the Green's operators. Another comment is what happens when the Hamiltonian is time independent. If partial of h is with respect to t is equal to 0, so the Hamiltonian is time independent, then we know that u of t comma t prime is actually a function only of the elapsed time. And in fact, it's given by e to the minus I h. It's really an operator h hat, the elapsed time t minus t prime divided by h bar. So there's a simplification in the form of the time evolution operator when the Hamiltonian is time independent. In fact, we abbreviate this notation and let's just write it as u of t minus t prime as a function of just the elapsed time. If we do this, then we can define a corresponding corresponding Green's operator. I'll just call it k hat of plus. And this is a Heaviside step function theta of t times u of t, like so, u hat of t. Or if I wanted to put in, I'll put in k minus also for completeness. This becomes minus theta of minus t times u hat of t. These are the two Green's operators, like so, written in operator language in the case in which the Hamiltonian is time independent. All right, that finishes all I want to say about time dependent Green's functions. Are there any questions about this? All right, if not, then I want to move on to time dependent Green's functions. I kind of hesitate to lecture on this because it takes time to do it, but I think it's good to have a physical picture of what these Green's functions look like, as I indicated a moment ago. For anybody that's thrown a stone in the lake knows what the outgoing Green's function looks like. So now what I'd like to do is give you an image. It's just by analogy with waterways, but it gives you a physical image of what the energy dependent Green's function looks like. Well, let me say some things about energy dependent Green's functions first of all. So they're used for solving the energy dependent Schrodinger equation. So we have E minus H acting on psi of X is equal to a source term S of X, like so. This is an inhomogeneous time independent Schrodinger equation. To solve this equation, we require a Green's function for the operator E minus H. And I'll call this Green's function G of X and X prime and energy E. It has to be parameterized by E because the operator on the left-hand side depends on E. Now, by the way, if the source term were equal to 0, then psi of X would be an energy eigenfunction, of the Hamiltonian H with eigenvalue E. In that context, E is actually an eigenvalue. However, when there's a source term out there, then E kind of loses that interpretation, and it becomes more like an energy like, let's call it an energy like parameter, which is allowed to take on any value whatsoever. In fact, in a minute, we'll see it even takes on complex values. It becomes a parameter of the problem, parameter of the Green's function, and what we see down here. So we'll think of this E as the parameter of the Green's function, as being an energy variable that's not necessarily an energy eigenvalue. Frequently, it's not. In any case, the Green's function G is required. The definition of a Green's function in this context is that it's a function such that if we let E minus H act on it, and by that we allow it to act on the field variables X and not the source variables X prime, that we get a right-hand side, which is a delta function of X minus X prime. There's no time delta function now because this is a time-independent problem. All right, now, if we find such a Green's function, then the solution to the original equation is that psi of X is equal to psi homogeneous solution of X plus an integral over dx prime of the Green's function G of X, X prime, and E of the source term S of X prime. And this is demonstrated in the same way. We apply the operator E minus H to both sides. On the left-hand side, we get E minus H acting on psi. The homogeneous solution is annihilated. The E minus H, bringing an integral sign, turns this into a delta function, allows us to do the integral, and we get the source term. So this is kind of standard Green's function stuff here, but now for the energy-dependent Schrodinger equation. So our goal in the next probably hour, it might take an hour of this lecture, but there isn't that much time left, it'd be less than an hour. The goal of the next phase of this lecture is to actually work out what the energy-dependent Green's functions are. Now, to do that, I'm going to concentrate on the geometrical picture and kind of short shrift the calculations. Some of the calculations are detailed, and you can read about them in the notes. But it may be that the physical pictures or the physical analogy will stick with you better and is maybe more important. So here's the idea in a water wave analogy. Here's the idea of the energy dependent Green's function. Well, in water waves, it won't be energy dependent. It will be frequency dependent. We'll have a Green's function G of X, X prime, and frequency omega. And here's what this means physically, is we have our lake here sitting out here like this, and we imagine that it's been quiet from the beginning of time up until t equals 0. And at t equals 0, we go to location x prime in the lake, which, remember, that's the source location. And what we do is we poke our finger in the lake at that point, but but instead of just doing it once, we continue to do it at a frequency omega. That's to say, we drive it with a term that goes like e to the minus I omega t, and we keep that up for the rest of eternity. So in other words, there's nothing going on at negative times, but at t equals 0, we start poking our finger in the lake at that point, and we keep on doing it forever. So now just imagine what's going to happen. You're going to have waves radiating out from your finger. Obviously, they're going to go out in all directions. Because you keep on poking forever, the waves are going to continue to radiate outwards. They may go over and hit the shore, they'll reflect, they'll bounce back, they'll interfere with the waves which are coming from the source being radiated. They'll get an interference pattern. In fact, you may get a rather complicated pattern like this. Nevertheless, after a while, what's going to happen is, well, let's see. Before I tell you what's going to happen, let me pose a simpler problem. You know, a lake, insofar as it can be modeled as a system that supports linear waves, is basically a big harmonic oscillator. It's got lots of normal modes, and they all oscillate at their eigen frequencies. A bunch of coupled oscillators, basically. That's the idea. So to simplify the physics of this, let's just imagine a single oscillator, single harmonic. This is like out of undergraduate mechanics now. So we got a single harmonic oscillator. Let's say it has native frequency omega 0, but we drive it at a frequency omega, like so. So a driven harmonic oscillator actually has two frequencies involved. Now the question then is, what frequency does the response oscillate? Is it at the natural frequency of the oscillator, or is it the driving frequency? If I were teaching in a class where I was giving lectures before a blackboard, I'd ask for a show of hands to see what people think about this. But since I can't do that, I ask you to just ask yourself that question: do you know the answer? And if not, think about it. Which is it? So anyway, here's what the answer is. If you take an harmonic oscillator with native frequency omega 0 and you drive it with a force at a different, possibly different, normally it is a different frequency omega, what happens is that for short times, the behavior is a linear combination of motions at both frequencies, omega 0 and omega. However, if the harmonic oscillator has damping, which real oscillators do, then the oscillations at frequency omega 0 eventually die out. And what's left over is just an oscillation at frequency omega. And that frequency, and that oscillation has a certain amplitude. Now, if you change the driving frequency and bring it closer to the native frequency of the oscillator, then and then again wait for the transients, which are the omega 0 frequency contributions, to die out, then you'll get again a steady state at frequency omega, but the amplitude will be larger. In other words, the steady state amplitude after the transients have died out grows larger and larger the closer you come to resonance. And in fact, if you drive it exactly on resonance, then what you find is that the amplitude is maximum for all possible values of omega. In fact, the only thing that keeps the amplitude from being infinite is the damping. So if you're driving it exactly on resonance, you're putting in a lot of energy, but because it's got high amplitude oscillations, that energy is being dissipated away by the damping. Well, the lake is like that, except it's got not just one normal mode, but it's got an infinite number of them. But the basic idea is that when you start driving it at t equals 0 at a frequency omega, and these waves form and so on, you're going to get a response of the lake, part of which is at the driving frequency omega, and part of which is linear combinations of the normal modes. But those normal modes will die out if the lake has damping, which real lakes do after a while, and those are the transients which will go away. And so if you wait for a long time, let's nominally you take the limit t goes to infinity, what you find is that the wave pattern on the lake is a constant wave pattern moving at a constant frequency, which is the same as the driving frequency. In other words, the wave pattern on the lake are at psi of x and t then. is equal to the driving frequency times some function that doesn't depend on time, it just depends on x. And so that's like, it's a standing wave, you see. Well, that function phi of x actually is the Green's function. It's g of x, x prime, and omega for explicitly putting in the parameters. So the Green's function in the lake, the Green's function is the wave pattern you get. If you start driving it at t equals 0 at frequency omega, you wait long enough for the transients to die out, then the wave pattern that's left, stripping off the common time evolution, which is given by the driving term, that is the frequency dependent Green's function. So that gives you a way of visualizing what it is. It's a standing wave that appears in the lake. By the way, if the lake opened out to infinity and became an ocean, then it wouldn't have ordinary normal modes. It would, because it would be in a continuous spectrum. And then the waves that you get obviously would just radiate out into the ocean. They'd go out to carry energy out to infinity, moving away from the source. You'd have waves going out like that. And that is the Green's function, in fact, in an infinite ocean. So that's something to keep in mind, because we're going to deal with the free particle Green's function in quantum mechanics, and we'll see it consists of a singularity, but also with outgoing waves moving away from the singularity. These will represent scattered waves in the scattering problem, as we'll see. All right. Anyway, with that water wave analogy, this water wave analogy is developed in more detail in the notes, but I don't want to take time to go into it. So I'll let you read about that. But this is enough. I want to give you. I think it's important to have this picture of what the Green's functions look like, so it's not just all empty formalism. By the way, speaking of the mathematical formalism of all of this, not only Green's functions but scattering theory. If you want to study functional analysis and spend some years of your life doing that, you can make all of this completely rigorous. My goal here is not to do that. I couldn't do it anyway. But my goal here is to give you physical models that will allow you to think about what's going on and give you good intuition for where you can go wrong on various kinds of problems. Because it's easy to do that by doing naive manipulations, integrating by parts and neglecting boundary terms and so on. There's a lot of things that can go wrong. All right. Anyway, so that's the purpose of the water wave analogy. Now, pursuing this water wave analogy further, if we wanted to apply this to the Schrodinger equation, let's think about having let's go back to the time-dependent Schrodinger equation with a source term, and let's make the source term s of x and t. Let's make it take place only for positive times. So I'll put in a Heaviside step function theta of t. So this is 0 for negative t. We'll make it spatially localized, so we'll put it at a location, let's call it x naught, so it's a delta function like that. And we'll give it a fixed time dependence, so that would be oscillatory time dependence, and that'll be e to the minus I et over h bar, where e is an energy-like parameter. By the way, to go back to the water waves, it's obvious you can drive the lake at any frequency you want. So omega is not an eigenvalue. It's a frequency parameter of the Green's function, which can be set to any value you want. You can drive the lake at any frequency you want. And likewise, this E here is not an energy eigenvalue, it's an energy-like parameter of, as it turns out, of the Green's function. So here the analogy is that in the water wave analogy, the omega is being replaced by E over h bar for the quantum problem. All right, let's suppose we take this as the source. Then what is the wave field that we get in response? Well, from our previous formula, oh gosh, let's see, can I find it? Because I'm not sure I said it right. Yeah, here's the formula. Here's the general formula for the solution of the inhomogeneous time-dependent equation, but we want to put in the k plus here. And somewhere I did that. Let me see if I can find it, because I want to make sure I remember to say some things. And yes, here it is. Here was the formula, but I explained that the causal solution has no homogeneous solution. So it looks like this. Well, let's take our finger poking in the lake, at a given frequency, and use that for the S here. And let's calculate the causal solution. We'll just apply this formula. So if we do this, then the psi is going to be, it's 1 over IH bars needed here. we have an integral from minus infinity to time t, dt prime. We have an integral over x prime. And then we have k of x, and oh, and by the way, I'm going to assume here that the Hamiltonian is time independent. So k depends on x and x prime, and then it's the elapsed time t minus t prime is a single time parameter that depends on. And then this is then multiplied by the source x prime t prime. Okay. Now, this source, on the other hand, we've got written it out just up above right here, but I need to put the unprimed, let me just put primes on things here on all the variables, and the variables in question. So if I do this, if I do it this way, take this s of x prime t prime and plug it in there, then we can simplify things. So the first thing to say is that psi of x and t is equal to 0 if t is less than 0. And that's because this is a causal solution, and this driving term doesn't switch on until t equals 0. If t is greater than 0, then psi of x and t is equal to what? Well, it's equal to this integral, but let's simplify it. In the first place, the theta of t prime means that the t prime, negative t prime, doesn't contribute. So this integral here only goes from 0 to t and not infinity, minus infinity to t. So I get 1 over I h bar, the integral from 0 to t dt prime, and that takes care of the theta of t part. The x prime integral I can do because of the delta function. So this gives me k evaluated at x, and instead of x prime, I have x0, comma t minus t prime. And then I have the time dependence here of e to the minus I e t prime over h bar, like so. Okay. So that's the wave field that's produced. Now, at positive times. Now, based on what we said in the water wave analogy, what we should expect as t goes to infinity is we ought to expect this to have the time dependence of the driving term minus e to the minus I e t over h bar, not t prime, but rather t, because it's the driving term. It's a time here. The times what's left over ought to be the Green's function. It ought to be g of x, x0, and energy e. And the question is that true? This has to be in the limit that t goes to infinity. Well, if we take this integral and we just do a change of variables, if we make tau is equal to t minus t prime, like this, then what we get here is we get psi of x and t is equal to 1 over I h bar, the integral from 0 to t d tau. This e to the minus I e t, I'll do the change of variables, so it becomes e to the minus I energy e times t minus tau over h bar. And then the k becomes k of x and x0 and tau. And you can see appearing here the actual time dependence. This is equal to e to the minus I e t over h bar. That's what we expect. That's the time dependence of the driving term, times the rest of it. And the rest of it is just reading off this integral, but omitting that time dependence. So if that's going to be the Green's function, then what we get is we get g of x and x0 and t, and energy e, is equal to the limit as t goes to infinity. Can we still see this? The limit as t goes to infinity of, I'm just going to copy this integral except leave off that phase factor, 1 over I h bar, integral 0 to t d tau, e to the plus I e tau over h bar, times k of x and x0 and tau. In other words, it looks like a one-sided Fourier transform of the time-dependent propagator. It's one-sided because the integral only goes from 0 to t is going to infinity. We're going to take upper limit to infinity. It's only going from 0 to infinity instead of minus infinity to plus infinity. But this is like making the energy an energy-like variable conjugate to time, and otherwise just Fourier transforming the time dependence of the time-dependent propagator. So very roughly speaking, we can say that the energy dependent Green's function is going to be the Fourier transform of the time dependent Green's function. But there's several wrinkles in this. It's not quite as simple as that. One of them is it's only a one-sided Fourier transform. And there's other wrinkles too, which I'm now going to point out to you. There's other things that make this not quite work. However, to get there, let's take these Green's functions here, both the G and the K, and let's replace them by operators. Let's write this, the left-hand side is the matrix element of G hat of energy E and X prime. Well, X0 here should have been, the X prime got converted into an X0. I'll call it X prime again. This then becomes the limit as T goes to infinity. If we believe this formula, 1 over I H bar integral 0 to T d tau e to the I plus IE tau over H bar. And then we have the matrix element here between X and X prime of the unitary time evolution operator U of tau. And so stripping off the X and X prime on the two sides and writing U of tau as e to the minus I H tau over H bar for the Hamiltonian, which we can do for a time independent problem. I'll put a hat on the Hamiltonian. What we get is the Green's operator G hat of E is the limit as T goes to infinity of 1 over I H bar, the integral 0 to infinity d tau e to the plus I E tau over H bar times e to the minus I H hat tau over H bar. Okay? So this is a formal expression involving operators, but you can combine these two exponents together to give you e to the I e minus h hat tau over H bar. And formally, at least then, this integral is easy to do. And the answer is going to be this. When you do the integral, you get limit t goes to infinity, you get 1 minus e to the I e minus h hat t over H bar divided by e minus h hat. Okay? Now here's the problem. So this is the answer. We can do the integral and we get an answer. But the problem is that this limit doesn't exist. This is the Hamiltonian here, H hat is shifted by an energy E. But the problem is that as T goes to infinity, this is like something just continues to oscillate up and down and never approaches a limit. I don't want to get into details of what it means to talk about the limit of an operator. But supposing we applied this operator to a wave function like one of the energy eigenfunctions, for example, then the operator can be applied to that because H hat acts on an eigenfunction, just brings out the eigenvalue. And if you do that, you can see that that wave function never approaches any limit as T goes to infinity because the phase factor just keeps oscillating. So following this idea from water waves, we end up with something that's not defined. And the question is why? Well, the reason is that in the case of the water waves, we assumed that there was damping, which caused the transients to die away. Those were the things that were oscillating at the frequencies of the normal modes of the lake. But the Schrodinger equation doesn't have any damping. And so the oscillations never die away. And that's what we're seeing here at this upper limit. If we try to imagine a lake without damping, then when we poke our finger in the lake like that, like I was explaining, the transients will never go away, and that's just the situation we have here. Instead, what we did was we assumed there was finite damping, which a real lake would have. Made the transients go away, and then we let T goes to that caused damping, and then we let T goes to infinity, which caused the transients to damp away. What's left over is the Green's operator, Green's function. If you'd done it in the reverse order, if you had let the damping go to 0 and then let T goes to infinity, you wouldn't get a limit, because if you let the damping go to 0, then there's no damping, and letting T goes to infinity, nothing dies out. In fact, that's the situation we've got here in the quantum problem, which has no damping. So to fix this up, we need to introduce some artificial damping into the Schrodinger equation. That'll be the strategy: introduce artificial damping, then let T goes to infinity, then let the damping go to 0, and then we will get the Green's function. So it'll work like this. to introduce damping into the Schrodinger equation, we take the usual Hamiltonian H hat, which is, of course, is a Hermitian operator with real eigenvalues. And let's replace it by H hat minus I epsilon, where epsilon is a small positive number. It's obviously a complex contribution here. If you do this and then you solve the time-dependent Schrodinger equation with the modified Hamiltonian, what you'll find is you'll get psi of x and t is the sum over the eigenstates Cn with coefficients, and then you get e to the minus I e sub n minus I epsilon t over h bar times the energy eigenfunctions, let me call them un of x, like so. It's just doing the usual normal mode, the usual eigenfunction expansion, except now there's this extra dependence in the time dependence. So minus I times minus I is minus 1. You see you get an overall time dependence here. It goes like e to the minus epsilon t over h bar, which goes to 0 exponentially as t goes to infinity. And as a result, this solution does damp out. So the suggestion is then that we take this H, our Hamiltonian, our real physical Hamiltonian, introduce this artificial damping, substitute it into this calculation we just did here. Here's the final result. Substitute it in there. Then we take the limit that t goes to infinity, and then we take the limit that epsilon goes to 0. So if I replace h by h minus I epsilon, look what happens to this exponent here. This becomes, this with a minus here. It's got a, I better write it on a new page. If I did the same calculation again, but just with h replaced by h minus I epsilon, what I get is this, is I get the limit as t goes to infinity, and I have 1 minus e to the I e minus h hat plus I epsilon t over h bar divided by e minus h hat plus I epsilon. And what you can see is that this limit actually is defined now because you have damping factors here because of the epsilon. So that makes this complicated exponential term go away, and the whole thing just turns into 1 over, I'll write it this way, is e plus I epsilon minus h hat. And so in a sense, what we get is we get a Green's operator G, which is correct, except it's not for the original energy E. It's for a modified energy, E plus I epsilon. And it's equal to the inverse of the operator E plus I epsilon minus H hat. And so this is an important result. We got what we wanted in terms of the limits we needed by introducing a small damping. And then, by the way, as I mentioned, since the limits don't commute, the first limit was t goes to infinity. Now we need to consider taking epsilon goes to 0 because the real Schrodinger equation doesn't have any damping. So that's the next task, is to look into that. Let's see. In the first place, there's a question about the nature of this operator, e plus I, 1 over e plus I. It's obviously the reciprocal of this operator, e plus I epsilon minus h. This operator is not Hermitian because it's got this imaginary part in it, but it does have a complete and orthonormal set of eigenfunctions, namely those of h. And in fact, it's really a function of the Hamiltonian operator. If we go to our formulas that we know for our procedures for defining a function of an operator, which we talked about in the very first week last semester, we know how to write this out in terms of the projectors onto the energy eigenstates and so on. So let's do that. Let's write that out so we understand what this operator means. Let's suppose our Hamiltonian has some discrete eigenstates. Let me call them n alpha, like this, bound states with energies E sub n. Alpha is an index used to resolve degeneracy. So this E and here are negative, like so. And let's suppose it's got a continuum, which I'll write this way, is equal to E times E times E alpha, like this, the eigenvalue, where this energy is positive, like so. And these satisfy orthonormality relations. N alpha scalar product with n prime alpha prime is delta n prime delta alpha alpha prime. The bound states are orthogonal to all the continuum states. And the continuum states E alpha scalar product E alpha prime is a Dirac delta function of E minus E prime times the Kronecker delta and alpha prime, like so. let's suppose we have a system like that. This would be fairly typical for a bound state problem with a localized potential, such as we'd use in scattering theory. Potential goes to zero at infinity. There's positive energy, not free, but positive energy solutions with a continuous spectrum, and negative energy solutions which are discrete bound states, which are normalizable. So let's suppose we have that. Then this operator G, which appears here, can be written in terms of those projectors in the following way. It becomes equal to the sum on the bound states in and alpha of the projector in alpha's outer product with itself. The projector is the outer product, divided by, this is parameterized by this, what is now looks like a complexified energy. So this becomes E plus I epsilon minus, and instead of having H hat in the denominator, replaced by the eigenvalue, which is E sub n. And then there's a continuum part, which is going to be an integral from 0 to infinity dE. That's the continuous eigenvalue for positive energies. And then we have the outer product E alpha. And now I have to say, oops, there's a problem, because this E here is actually the energy parameter of the Green's operator, whereas this E is a variable of integration. I want to keep them distinct, so let me put a prime on the variable of integration, which is part of the resolution of the identity. Then in the denominator, I have the E plus I epsilon, which is the same as that E plus I epsilon right there. And then the H hat gets replaced by the eigenvalue, which is E prime. So in any case, this then becomes an expression, a formal expression anyway, for the Green's operator, expressed in terms of the eigenstates and projectors of the Hamiltonian under these assumptions. There's a discrete part due to bound states and a continuous part. Now, one of the things to notice is that if the imaginary part, if the damping is non-zero, so that epsilon is positive, is that none of these denominators is equal to zero. So there's never any problem with a vanishing denominator. And glossing over details, let's just say that makes this G of E a relatively nice and well-behaved operator. So the point to make is that it's well-defined. It's a well-defined operator. On the other hand, we're going to be interested in letting epsilon go to zero, because the real Schrodinger equation doesn't have damping. So we need to think about that. It's important in doing this not to just substitute epsilon equals to zero. Rather, you need to take the limit and do it right as a limit rather than just substitution, because the substitution, in fact, doesn't work. If I substitute epsilon equals to zero, then on this integral over here, if the energy parameter E is positive, then that means this E minus E prime denominator goes to zero over some range of, or at some point in this range of integration in E prime. And it turns out that integral in that case is simply not defined. So just substituting epsilon equals zero won't work. At least it won't work for positive energies. Okay. On the other hand, the limit is defined. The limit is epsilon goes to zero, and we'll actually evaluate that at some point, probably not tonight.
Could I ask a quick question?
Yes.
So is this formula that you just wrote down for the Green's function operator, is it true for both outgoing and incoming Green's functions?
Well, I've told you, I've explained outgoing and incoming Green's functions for the time-dependent Schrodinger equation.
Okay.
And yes, I see your point. But the Fourier transform that I took here was the outgoing Green's function. So this is what I'm doing here is actually attached to the outgoing Green's function.
Right.
And in fact, at some point, I'm going to call this a G plus for that reason.
So
yes.
we'll have,
Yes.
okay. Sorry.
Yes.
So we'll have a corresponding similar function to the incoming.
Yeah, you'll have a G minus also. However, that water wave analogy that I gave you applied to the outgoing only, because remember, you're poking your finger in the late starting at T equals zero and looking at the waves that are radiated. That's the outgoing stuff. And we use the outgoing Green's function, you know, to plug in the source term to get these formulas. So this is at this point I'm following the outgoing version of the energy dependent Green's function. But you're quite right. There's going to be two different versions of them, plus and minus.
Okay.
Which we'll get to maybe before the night is out tonight.
Thank you.
All right, good. All right, good. Now, okay, so the formula is well defined if epsilon is non-zero. Now, so far, I haven't proved anything. I haven't proved that this G in the limit that epsilon goes to zero is a Green's operator. I need to do that. All I've really done is just invoke this image of the water waves and then follow the formula as if we try to do something similar with the Schrodinger equation, and then deal with the obstacle that we had to, we didn't have damping, so we had to put that in, all that to take these limits. Okay. But so far, I really haven't proved anything. I've just given some chain of talk, which leads to an interesting formula. But we are going to be interested in what happens as epsilon goes to zero. So let's look at the behavior of this expression as epsilon goes to zero. So to do that, let me draw an energy axis for the real energy. It's actually energy complex plane. Let's draw it like this: imaginary energy and real energy, like so. This E plus I epsilon, sometimes I'm going to write this as Z equals E plus I epsilon to represent a complexified energy. And right now we're going to be interested in the case where the imaginary part of Z is positive. We're in the upper half plane. If we do this, then this can be regarded as G plus of Z. You see, that's just another way of writing it. So G plus of Z is defined in the upper half plane. That's what I was just saying a minute ago about the denominators don't vanish. What happens when we let epsilon go to zero? Well, let's suppose we have this kind of typical spectrum. So we've got some bound states at negative energies like this, and then starting at E equals zero, we've got a continuum that goes out like that. Let's suppose that's the spectrum of the Hamiltonian, common in practice. I'd like to take 3 different cases here. Let's take case A, in which the E plus I epsilon is sitting above a gap between the eigenvalues of the discrete spectrum. And let's take epsilon equals to zero so that we approach the real axis like that. Then let's look at what happens. So this E here that I'm speaking of, this energy parameter, its real part E is negative. For in case A, the real part of E is negative, like this, and E is not equal to any eigenvalue En. That's case A. Well, now look at this. Let's look at first of all the integral here over positive energies. The E prime is just positive energies, but the E is negative. And so the denominator E minus E prime never goes to zero. And you can just let epsilon go to zero and it doesn't change that. So this integral here is actually well defined. There's no problem with doing this integral. As far as the first term is concerned, we're assuming that E is in the gaps. So E is not equal to any of the E sub n's. And so once again, this denominator E minus En is non-zero for all values of n. And letting epsilon go to zero, again, just gives you a reasonable expression with no vanishing denominators. And so the result is that in case A, the limit as epsilon goes to zero of G, I'll call it G plus now, of E plus I epsilon exists, and let's just call it G plus of E. We can call it that, okay? All right, now, let's take case B, where we're exactly on an energy eigenvalue. And the difference is that in case B, one of these terms, the E is going to cancel the E sub n for one of these discrete energy eigenvalues. And therefore, as epsilon gets smaller and smaller, the denominator goes to zero, and this term goes to infinity. And so in case B, what we find is that the limit does not exist. Epsilon goes to zero, does not exist. However, it diverges. You see, it goes to infinity, and because of these bound state terms. However, it's easy to see that if epsilon is small, then one of these discrete bound eigenstates is going to dominate the sum. And in fact, so for small epsilon, what this is going to look like is that the G plus of E plus I epsilon is going to look like 1 over I epsilon times a single term, a sum on alpha of the projector in alpha n alpha. Well, that projector in alpha n alpha, this sum is the projector onto the eigenspace for eigenvalue n. So if you're coming down onto an eigenvalue E sub n, what happens is when you get close to it, the Green's operator blows up, but it blows up in such a way that it becomes dominated. The closer you get, it becomes dominated by the projector onto that eigenspace. Okay. Now finally, let me take case C, where we're in the continuous spectrum. We come here and we come down like this. What happens then? In case C, well, in case C, the both E and E prime, E is a fixed number which is positive, that's where we're coming down from, and the E prime is a variable of integration that goes over the entire positive axis. So we run right over the place where E prime equals E. And as epsilon goes to 0, that denominator gets smaller and smaller. So so in the limit, the integrand has a singularity. I kind of pushed it off the page. It turns out, in spite of that, nevertheless, that the limit exists. And this is something I won't prove, but we'll see an example of it, is that the limit exists in that case. And so what it gives us is a G plus, it's a G plus operator of E now for positive energy E positive. And as I say, we'll see an explicit example of that. All right. So to summarize, with the Green's operator defined for essentially complexified energies in the upper half of the complex plane, call them G plus of E. This Green's operator is well defined as we let epsilon go to 0, as long as the energy E is not equal to any of the discrete eigenvalues of the bound states. Otherwise, the operator is defined. It's defined for the continuous positive spectrum, and it's defined in the gaps in the negative energy discrete spectrum. Okay, so that's the G plus. Now, this is all great, but now the question is it really a Green's operator? Well, a Green's operator would satisfy the equation that E minus H hat, I'll put it, make it as an operator. Well, in terms of Green's functions, let me go back to that first. It's E minus H, where H is the differential operator. You'd have G of X prime and energy E should be equal to Dirac delta function of X minus X prime. That's the equation that a Green's function has to satisfy. If we map this into the language of Green's operators, it becomes E minus H hat times G hat of E is equal to 1. That's to say 1 times, excuse me, it's equal to the delta of X minus, yeah, no, excuse me, it's equal to 1. I didn't say right, it's equal to 1. It's equal to the identity operator. I'll just put it as a 1, kind of a boldface 1 there. It's the identity operator. You can see that because if I sandwich this on the two sides with the X and the X prime, then the matrix elements of 1 is just the Dirac delta function. That's where that comes from. But an operator language is just this. This, by the way, would lead you to believe that the Green's operator is the inverse of E minus H hat. And that's almost true, but it's actually, the actual details are much trickier than that, which is why I'm going through these epsilon equals 0 stuff. All right, in any case, let's now check that the G plus at which we have defined, let's define, so let's do it this way. I'll outline it. We want to define G plus as an operator of energy E is equal to the limit as epsilon goes to 0 of G plus of E plus I epsilon, which works as long as E is not equal to any En. All right, so let's make that definition. And then let's look at E minus H hat acting on G plus of energy E, and let's see if it satisfies the Green's function equation. So this is E minus H hat times the limit as epsilon goes to 0 of 1 over E plus I epsilon minus H hat. And that's equal to the limit as epsilon goes to 0 of E plus I epsilon minus H hat minus I epsilon divided by E plus I epsilon minus H hat. You see, I just added and subtracted I epsilon in this factor and just brought it in the numerator here. These are operators, but we don't have to worry about the order of the multiplication or division because they're all functions of the same operator H hat, so they all commute with each other. In any case, the first term here, so this gives you the limit as epsilon goes to 0 of 1 for the first ratio here, minus I epsilon divided by E plus I epsilon minus H hat. So I epsilon is just a constant, a number, it's just a number. Multiplying this 1 over E plus I epsilon minus H hat, whose limit as epsilon goes to 0 is G plus of E, defined when E is not equal to any En. So if E is not equal to any En, then this second term is I epsilon times G, which is well defined. But the epsilon is going to 0, so it's going to force that second term to 0. So what we can say is that this just becomes equal to 1 if E is not equal to any En. So in other words, if the energy, so let me summarize this here, is that if the energy parameter E is not equal to a discrete energy eigenvalue, then the G plus of E defined in this way actually is a Green's function for the energy dependent Schrodinger equation. Okay, I could write that out. I could write that out in words, but that I could write that out on paper. But those are the words that goes along with it. All right, now, we're essentially out of time. But we're also, as typical, we're right in the middle of this analysis. So what we've done is we've actually have derived at least an outgoing energy dependent Green's function, which is defined for all values of real energy except for discrete energy eigenvalues. And this therefore can be used to solve the inhomogeneous time independent Schrodinger equation when the energy parameter is not equal to an energy eigenvalue. And it's one of other possible collection of Green's functions. This is the outgoing Green's function. So where I want to go next with this is I want to look at the other case of the incoming time-dependent Green's functions. We'll do essentially the Fourier transform of that, and we'll get a second energy-dependent Green's function for the energy-dependent problem. We'll call it G minus. It'll be a G plus and a G minus. Now, the interesting thing about G plus and G minus is that both of them begin as being defined in the complex plane. G plus gets defined originally in the upper half plane, and turns out G minus gets defined in the lower half plane. They both have limits as you approach the real axis, as long as you avoid the discrete eigenvalues. And in the places where they, in the gaps between the negative energy eigenvalues, you find the two limits are the same. And what this means is that the G operator is the G plus on the upper side and the G minus on the lower side are actually analytic continuations of one another through the gaps between the discrete energy eigenvalues on the negative energy axis. In a sense, if you think about this Green's operator as a function of a complexified energy, it becomes a function of a complex variable, the complex energy, which is analytic in the entire upper half plane and in the lower half plane, and are analytic continuations of each other. On the other hand, at the discrete eigenvalues, it turns out they have poles. These are the divergences which occur as you approach the discrete eigenvalues. And for the positive energy axis, it turns out you have a branch cut, which means that the limits from the two sides are not equal to one another, but there's a discontinuity across them. And so these are the topics which I'll take up next time, which is going to be, I guess, next Tuesday. Okay, with a little preview of what we'll do. Okay, so that's all for tonight. Are there any questions about this? Typical physics books in describing energy-dependent Green's functions, they say, oh, there's a prescription. We just replace E by E plus I epsilon, and that takes care of singularities. And they just wave their hands, and you're supposed to go with that. Well, you can't understand. I don't think most of the stuff that's presented in physics textbooks about Green's functions is actually comprehensible at any level. So I'm trying to make this at least comprehensible. I'm trying to make the logical steps plausible at least. Okay, well, if there's no more questions, then I will stop screen share. One last chance for a question before I turn off the recording. Okay, here we go.